Lighthouse Scientific Education presents a lecture in the Atomic Structure series. The topic, Electronic Configuration, Part 1. Material in this lecture builds upon the previous lectures, Atomic Basics, and Quantum Mechanics. The lecture will begin with a review of the basics of the Quantum Mechanics lecture. If a student feels comfortable with this lecture, then skip to the next topic. Building electronic configurations. EC or ECs will be used as a shorthand in this lecture for the term electronic configuration. The building begins at the topic selection, Electronic Configuration Energy Levels. This is the first of two procedures for producing electronic configurations, EC. The second procedure requires the use of the periodic table of elements. From there, we will reverse the process and practice obtaining an element or atom from an electronic configuration. As a heads up, for what's covered in the second lecture on this topic, Electronic Configuration Part 2, there are two topics. The first is a look at the exceptions to the general process for getting electronic configurations. And the second is expanding the process to get ion ECs. There is also a section where we practice these procedures with a quiz. The quiz can be viewed by itself following this lecture. Before we start, it should be noted that this is a long and involved lecture topic. It is so because our lecture is designed to provide the rationale for why ECs are structured the way they are, and because it uses repetition to train the students to utilize the processes. Since the topic in our lectures are covered in depth, we may be covering it more thoroughly than is covered in your class. Be aware of the level of understanding that is expected of you and view this lecture accordingly. Oh, and be sure to have a copy of your periodic table of elements handy. Central to electronic configurations are the quantum numbers. These mathematically produced values provide a way of assigning each electron in an atom to a region, we'll call them orbitals, which is around or about the atom. An atom's electronic configuration is the assignment of every electron to the most appropriate orbital. As such, much or all of the area around the nucleus will be assigned one or more orbitals. The four types of orbitals based on the angular quantum number L are the s orbital, which are spherical, L equals 0, p orbitals, which are dumbbell-shaped, L equals 1, and the d and f orbitals, which we will refer to as multiple-lobed, L equals 2 and 3, respectively. Orientation in space of an orbital is based on its magnetic quantum number m. There is one orientation for s orbitals, 3 for p, 5 for d, and 7 for f-type orbitals. The principal quantum number n represents the general energy level of a set of orbitals. That is, the larger the n, the larger the orbitals, and the higher energy of electrons occupying those orbitals. As n increases, new rounds of orbitals are added to the energy level. When n equals 1, L has one type of orbital, just the one spherical s orbital, 1s. The 1 in 1s signifies that it is an orbital of the energy level 1. For the n equals 2 energy level, there are two types of orbitals added. n equals 2 has its own s orbital, 2s, which is larger than the 1s, and has a set of 3 equal energy p orbitals, the 2p orbitals. The 2 signifies that these orbitals are of the energy level 2. For the n equals 3 energy level, there are 3 types of orbitals added. n equals 3 has its own larger s and p orbitals, 3s and 3p, along with a set of 5 equal energy d orbitals, the 3d orbitals. For the n equals 4 energy level, there are 4 types of orbitals added. n equals 4 has its own larger s, p, and d orbitals, 4s, 4p, and 4d, along with a set of 7 equal energy f orbitals, the 4f orbitals. There are energy levels going up to 7. All of these levels will have s and p orbitals, but not all will have d and f orbitals. The orbitals can be ranked by relative energy, as shown by the periodic table of elements. For completion purposes and to familiarize ourselves where orbitals map to the table, we should verify that. Beginning with the version of the periodic table that has the orbital blocks already mapped onto it, we can create the ranking by relative energy by simply reading out the orbitals as they appear on the periodic table. That is, moving across and then skipping down a row. Remember that the elements in the 4 and 5F blocks are really inserted in front of the 5 and 6D blocks respectively. Let's begin. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, and 5f, 6d, and 7p. The process of relating electronic configurations to element is made dramatically easier with an understanding of where the orbital blocks map onto the periodic table. The quantum mechanics lecture covers this in depth. Moving on to electronic configuration, energy levels. If we stratify the orbitals by relative energy, that is, by increasing energy level, lowest to highest, we will get this common structure for demonstrating electronic configuration. A stratified energy level diagram. Most textbooks use a diagram like this, or they have similar ones that keep the orbitals in order but shove them all the way to the left-hand edge. Either way, the orbitals are ranked by increasing energy. At the bottom is the single 1s orbital. It is represented by a single box. A bit higher, we see the 3 2p orbitals. They are represented by 3 boxes, which are at the same energy level. Jumping up even higher, we find the 5 boxes that represent the 5d orbitals of the n equals 3 energy level. Each of these 5d orbitals have the same relative energy, which is why they are all on the same line. Our initial tour ends up at the 7 boxes that represent the 7 equal energy f orbitals, the 4f orbitals. Note that the distance between neighboring orbitals gets smaller as the energy levels get larger. That will be important later. We can take a sneak peek at what an electronic configuration would look like on this diagram using the element nitrogen. We can also have said nitrogen atom, and it wouldn't have really made a difference. Its atomic number is 7, which means that it has 7 positively charged protons. Since atoms are neutral, nitrogen needs 7 negatively charged electrons. They're represented here by 7 arrows. Here is how those 7 arrows fill this diagram. There are 2 rules that explain this result. The first is the Hund's rule. Each orbital can be assigned a maximum of 2 electrons. Each box can hold 2 electrons. More specifically, the electrons must be of opposite sign, plus 1/2, minus 1/2. It's called paired spin. That is why some of the arrows, electrons, are pointing up, plus 1/2 spin, and some are pointing down, minus 1/2 spin. The second rule is the Aufbau, or build-up principle. Add electrons starting at the orbital with the lowest energy. In nitrogen's electronic configuration, the first 2 of the 7 electrons were put into the 1s orbital. Their spins were paired, 1 up and 1 down. There's not really an order to the 7 electrons of nitrogen. When we say something like the first pair of electrons, it refers to 2 of the 7 electrons in the process of building electronic configuration. We really have no idea which of the 7 electrons ends up in the 1s orbital. Also part of the principle notes that when an orbital is filled, go to the next lowest orbital. After the first pair of electrons was added to the 1s, the second pair was added to the 2s. The Aufbau principle continues this process until there are no more electrons. Though there's one more consideration. Add electrons to all equal energy orbitals before any pairing. The three 2p orbitals have different orientations, but they have the same relative energy. 2px equals 2py equals 2pz. So after filling the 1s and 2s orbitals, the three remaining electrons are added to the next lowest energy level, and that is the 2p orbital. Each of the three boxes gets an electron. More on that phenomenon later. Now it's time to build up some electronic configurations. We will start with the smallest atom and move along the periodic table. Multiple examples will highlight and reinforce the use of these rules. Hydrogen. It has one proton and one electron. The Aufbau principle says the lone electron goes in the lowest energy orbital, the 1s. And we're done. Hydrogen has been assigned an electronic configuration. Though in addition to assigning electrons to orbitals, we want to develop a written format that demonstrates the electronic configuration. And for hydrogen, it is 1s1. The first one is the principal quantum number n of the orbital in the configuration. That's followed by the orbital type. It's an s orbital here. And a superscript attached to the orbital type is the number of electrons in that orbital. As we move forward to larger atoms with many electrons, this written format describing the EC will include more and more energy levels and more orbitals. However, that will have to wait because our next atom only has one more electron than hydrogen. It's helium. It has two protons and two electrons. According to the Aufbau principle, its first electron will go into the 1s orbital, like the one electron in hydrogen did. Since the 1s orbital can hold two electrons, and we have only added one so far, we will add the second electron to the 1s orbital. Importantly, according to Hund's rule, two electrons in an orbital must have opposite spin. We're not expected to really know what the spin is on an electron, but we do know that they have to be paired in an orbital. So to generate a proper electronic configuration, we just have one arrow point up and the other point down. The written format of the electronic configuration will be 1s2. The 1s orbital has two electrons in it. And we've come to our first electronic configuration of a noble gas. This is important because we will see that the electronic configurations of noble gases are the most stable configuration on the periodic table. Much of chemistry can be viewed as atoms trying to obtain the electronic configuration of their nearest noble gas. More on that when we get to the octet rule and the building of compounds and molecules. For now, we need to introduce a shortcut in the format of writing electronic configurations. It involves writing noble gases, or the configuration of noble gases, as an abbreviation. The 1s2 designation of helium can take the form He in square brackets. 1s2 and brackets He means the same thing. The next element is lithium. It has 3 protons and 3 electrons. The first electron goes into the lowest energy orbital. The second is paired with the first in the now filled lowest energy orbital. There's one more electron to go. Where should it go? Well, according to the Aufbau principle, when an orbital is filled, go to the next lowest energy orbital. That's the 2s, and now we have assigned all of the electrons. What is the written format for this configuration? 1s2, 2s1. There is one electron in the 2s orbital. Another way of writing this is using the brackets He for 1s2. Moving along the periodic table to beryllium, it has 4 protons and 4 electrons. The first 2 are paired in the lowest energy orbital. The next one goes in the 2s orbital, and the 4th electron, like we saw with the addition of the second electron in helium, is paired, opposite spin. Its EC is written in the format 1s2, 2s2, or brackets helium, 2s2. It should start to become apparent that as we move along the periodic table, by one element at a time, we are simply adding one electron to the EC of the previous element. Maybe this isn't so hard after all. So, boron with its 5 protons and 5 electrons should have a similar EC to beryllium, except we need to find a place for that extra electron. 2 paired electrons go in the 1s, 2 paired electrons go in the 2s, leaving 1 electron to go in the next lowest energy orbital, the 2p. By convention, the electron is added to the box on the left. But since all 3 of the 2p orbitals are of the same energy, it doesn't really matter. Its EC is 1s2, 2s2, 2p1, or brackets helium, 2s2, 2p1. There is 1 electron in the 2p orbital. Note that in the written format of the EC, there is no reference to which of the 2p orbitals has the electron, or even if it has a positive or negative spin. That information has to be deduced from the rules of the process. With carbon and its 6 electrons, we will be faced with a new decision for that last electron. 2 paired electrons in the 1s, 2 paired electrons in the 2s. The first of the 2 remaining electrons will go into the 2p, like boron. Where does that last electron go? Remember the Aufbau principle. Add electrons to equal energy orbitals before pairing. The 3 2p orbitals, 2px, 2py, and 2pz, have equal energy, so add the last electron to a different 2p orbital. And again, by convention, the arrow is added to the second box and given the same spin as the first. That's just how it's done. Looking at the written EC, 1s2, 2s2, 2p2. We see 2 electrons in the 2p orbital, but again, no details as to how they're distributed. That's okay. If we know how to build configurations, we will know what that 2p2 means. We should start to feel comfortable using the brackets helium in place of 1s2. There is more EC building to come, but here's a good time to bring in the periodic table of elements and show how to find an atom given an electronic configuration. Say we're given the electronic configuration 1s2, 2s2, 2p2. Yes, we just produced that for carbon, but let's act as if we didn't know what it was. The key to determining the element, or atom, this EC represents is in the last orbital in the EC. Here it's 2p2. We spent a fair amount of energy in the quantum mechanics lecture mapping orbitals onto their blocks on the periodic table of elements, and this is why. If we can find the 2p orbital block on the table, we're halfway there. 1s2, 2s2, 2p. It's in this row. We will find the appropriate element in that row by counting over as many elements as the superscript of the last orbital in the EC. Here, it's a 2. And 2 elements over from the front of the 2p orbital block is the element carbon. We will practice this procedure a couple more times in this lecture. Now back to the stratified diagram and more ECs. Nitrogen. We practiced with this element earlier. It has 7 protons and 7 electrons. The first pair goes in the 1s, the second pair in the 2s. Each of the remaining 3 electrons goes into its own equal energy 2p orbital. All the arrows pointing up. Again, it's just convention. No pairing. The 2p orbitals are said to be half filled, 1 electron in each. Fully filled means 2 electrons in each. 1s2, 2s2, 2p3. Now oxygen. Let's pick up the pace a little bit. 8 protons and 8 electrons. The first pair goes in the 1s, the second pair goes in the 2s. 3 electrons go into their own equal energy 2p orbitals, and that leaves 1 electron. The 2p orbitals are only half filled, So we are not done with them. It would be a mistake to put the last electron in the next lowest energy level, the 3s. Instead, we're going to start pairing the 2p orbitals because each can hold 2 electrons. And yes, by convention, we will start with the one on the left. 1s2, 2s2, 2p4. Fluorine, 9 protons, 9 electrons. The first pair goes in the 1s, the second pair in the 2s. 3 electrons go into their own equal energy 2p orbitals, leaving 2 electrons. The first electron pairs with the first of the 2p orbitals. The second electron pairs with the second 2p orbital. 2 of the 3 2p orbitals are filled. The last one is half filled. 1s2, 2s2, 2p5. It looks like one more electron will produce a fully filled set of 2p orbitals. But first we're going to take this EC to the periodic table of elements and practice our skill at matching an EC to its element. And the key is the last orbital in the configuration with its superscript. And in this example, it's 2p5. As we saw with carbon example, the 2p block is located at this row. Checking the superscript of the 2p, we see that we need to move 5 elements from the start of the block. Fluorine, of course. Back to building ECs. And this time it's for the noble gas neon with its 10 protons and its 10 electrons. The first pair goes in the 1s, the second pair in the 2s. 3 electrons go into their own equal energy 2p orbitals, leaving 3 electrons to pair and fill each of the 2p orbitals. 1s2, 2s2, 2p6. This time, however, we're not going to use that bracket helium shortcut. Like helium, neon is a noble gas. So we can use the bracket neon for 1s2, 2s2, 2p6, just like we use brackets helium for 1s2. The same shortcut is available for other noble gases. When an element has 18 or more electrons, the brackets argon shortcut can be used. When an element has 36 or more electrons, the brackets krypton shortcut can be used. And this follows down the table. We have seen how to produce electronic configurations for the first 10 elements. ECs for most of the rest of the elements are done the same way. We'll take a look at a few more to make sure we understand the process. Magnesium. It has 12 protons and 12 electrons. The first pair go in the 1s, the second pair in the 2s, the next 6 go into the 2p. There are 2 remaining electrons. The first goes in the 3s, and the second pairs, opposite spin, with the first. The 3s orbital is filled. 1s2, 2s2, 2p6, 3s2. We can also use the brackets neon 1s2, 2s2, 2p6. Let's take this EC to the periodic table and show how it maps to magnesium. Seeking our key, the last orbital in the electronic configuration, we have 3s2. Begin by finding the 3s block. 1s, 2s, 2p, and here, the 3s orbital block. So we know this element with this EC is in this row. Noting the superscript in 3s2 is indeed a 2, we simply count over 2 elements from the start of the 3s block. Magnesium. Back to ECs. Moving down the row a bit, we have sulfur with its 16 protons and its 16 electrons. The first pair go in the 1s, the second pair go in the 2s, the next 6 go in the 2p, the next 2 go in the 3s. There are 4 remaining electrons. We saw a similar breakdown with oxygen. It is 1 row above sulfur on the periodic table. After filling the 2s orbital, it had 4 more electrons, and the next lowest energy level was a set of p orbitals. Not surprisingly, sulfur will distribute its 4 electrons in the same manner. That is, since each of the 3 3p orbitals are of the same relative energy, each will get 1 electron, making them half full, before pairing with the last electron. 1s2, 2s2, 2p6, 3s2, 3p4. Since we use oxygen as an argument for how to distribute the last 4 electrons of sulfur, we should make a comparison of their ECs. Note the similarity of the distribution of the last 6 electrons, 2 in the s, 4 in the p's. This highlights the period nature of the periodic table of elements. Down a column, the elements have similar electronic configurations. The difference is that a new set of energy levels is added going down a row, so the distribution of the last few electrons employs similar types of orbitals, but with a larger n value. More striking is a comparison of these two ECs using the noble gas shortcuts. It is these electrons that come after those that make up the noble gas shortcuts that participate in the majority of chemical reactions. Oxygen and sulfur are in the same column of the periodic table because they have similar electronic configurations and therefore undergo similar types of chemistry. That's why ECs are so important. We'll wrap up developing ECs with a look at argon. 18 protons and 18 electrons. The first pair goes in the 1s, the second pair in the 2s, the next 6 go into the 2p, the next 2 go in the 3s. Of the remaining 6 electrons, 1 goes into each of the 3p orbitals before pairing with the remaining opposite spin electrons. 1s2, 2s2, 2p6, 3s2, 3p6. Noting that argon is a noble gas, we can shorten 1s2, 2s2, 2p6, 3s2, 3p6 to bracket argon. If you don't feel comfortable with how we develop the electronic configurations of these elements, back up and watch again. Moving forward, while many instructors want their students to have a certain level of competency using this stratified orbital diagram, the goal is to be able to obtain and use ECs. A similar and ultimately easier method for building electronic configurations uses the basic steps we have just covered, but does so on the periodic table. To get the EC from the periodic table, the student needs to understand how to assign the orbital blocks to the table shown here. Once that is mastered, the rest is really just counting. Earlier we saw the EC of carbon as 1s2, 2s2, 2p2. The first step in getting this configuration from the table is locating the element and noting its atomic number, 6. Our objective is to assign carbon's 6 electrons to the orbital blocks much in the same way that we did with the stratified orbital diagram. Hund's rule and the Aufbau principle still apply. That means we will fill the lowest energy orbitals first with 2 electrons and proceed until we get to the element. Here we go. 2 electrons go into the 1s orbital, 1s2. 2 electrons go into the next lowest energy orbital, the 2s orbital, 2s2. We have 2 more electrons, and they are going to go into the next lowest energy orbital, and that is the 2p, 2p2. The nice part of assigning an EC this way is that we don't have to concern ourselves with how those last 2 electrons are distributed in the 3 2p orbitals. The EC does not explicitly contain that information. It's in there by understanding the Aufbau principle. Let's try another. Magnesium. We locate the element on the table. Its atomic number is 12. It has 12 electrons. It is in the 3s orbital block, so the electronic configuration is going to end with 3s. All right. Starting at the lowest energy orbital, From the perspective of the table, top left. 2 electrons go in the 1s orbital. Reading the table like a book, left to right and down a row, the next lowest orbital, 2s2. Then 2p, and that gets 6 electrons, 2p6, leaving 2 electrons. The 3s orbital, 1s2, 2s2, 2p6, 3s2. One more time. The noble gas argon with its 18 electrons. Locating argon on the table, note that it is in the 3p block, meaning the last orbital in its electronic configuration is 3p. And we begin the electronic configuration with the lowest energy orbital. That's at the top left. 1s2, 2s2, 2p6, 3s2, leaving 6 electrons, which fit nicely into the 3p orbitals. 1s2, 2s2, 2p6, 3s, 2, 3p6, or just brackets argon. A quick look at a table containing the first 18 elements listed by atomic number can help reinforce the process of producing ECs. We can see that when viewed in order of atomic number, an atom electronic configuration is really just adding one more electron to the highest energy orbital of the preceding or previous element. If that orbital is filled, add the electron to the next lowest unoccupied energy orbital. Looking at the last orbital in the configuration, 1s orbital gets filled, then 2s orbital, followed by the 6 elements that fill out the 2p, back to 2 elements for the 3s, and finally the 6 elements fill out the 3p. The electronic configurations for noble gases are used as a shorthand abbreviation: helium, neon, and argon. Let's recap this very busy lecture. An atom's electronic configuration, we've been calling it an EC, is the assignment of every electron to the most appropriate orbital. Quantum numbers provide a way of assigning each electron in an atom to a region or an orbital around the atom. The s orbital is spherical, there's 1 type. P orbitals are dumbbell shaped, there are 3. D and F orbitals are multiple lobed, there are 5 and 7 types respectively. The Aufbau principle helps us assign an atom's electrons to orbitals. It says to begin by adding electrons to the orbital with the lowest energy. When the orbital is filled, go to the next lowest energy orbital. Add electrons to equal energy orbitals before pairing. For example, 2px, 2py, and 2pz are all of equal energy, and electrons are added to each before any pairing. Hund's rule says each orbital can hold up to 2 electrons of opposite spin, plus 1/2, minus 1/2. We used up and down arrows to represent the positive and negative spin. We can find an element from its EC by using the last highest energy orbital, example 2p5. Locate that orbital, 2p, on the periodic table and count over, from the left, the number in the superscript, the 5th element of the 2p orbital. Remember that there is a second part to this lecture. It contains exceptions to the general process for getting electronic configurations and ion electronic configurations. It also has a practice quiz, which covers the different types of questions that can be asked of this material. Students can take this quiz now if they want. And that concludes part 1 of our lecture on electronic configurations. Make these new ideas an asset with a little practice.